Hey everyone, I hope you're doing well today. In this video, let's talk about simplifying radicals. If you're learning about how to simplify radicals, then I'm assuming you know a little bit about powers. Here on the screen to the left side of the equal sign, you can see an example of a power where b is equal to the base and the I is the exponent. Specifically in this video, the exponent or I is going to equal 2, and when you take a number raised to the second power, or squaring it, then a on the other side of the equation is going to be a perfect square. For the purposes of this video, when b is a positive number and we raise it to the second power, or I is equal to 2, then we get a perfect square on the other side, which is equal to a. For example, if we had 7 to the second power, or 7 squared, that's equal to 49. The base would be 7, the exponent would be 2, and 49 is a perfect square. Now that we've done a little refresher on exponents and powers, now let's talk about radicals. You should really think about radicals as the inverse of exponents or powers. Imagine we have some number a, which is a perfect square, and it's under this thing called a radical, which kind of looks like a long division symbol, but is a little bit different. Just outside to the left of this radical is this little number that's going to be called the index. And whenever you don't see an index, you can always assume that it's an invisible little 2 that's hiding out there. That just means we're taking the square root of what's inside of the radical. So basically, when I is equal to 2, or you don't see a number outside to the left of it, or you don't see an index, then b would be the square root of whatever a is. So when you look at the square root of 49, remember that the index is 2, it's just invisible, this is just going to equal 7. The little 2 just means we need 2 7s multiplied together to get 49. While I just gave you one example of a perfect square like 49, keep in mind that the number inside the radical doesn't always have to be a perfect square, and that's going to be the point of this video on simplifying radicals. A key takeaway you want to have from this video is the fact that perfect squares are really just the area of squares. When you have a square, the base and height, or the length and width, are the same dimension, so when you find the area of it, it's just equal to a perfect square. While you might not know a lot of perfect squares off the top of your head right now, with some practice you'll start to memorize them over time. While there's an infinite number of perfect squares, here are the first 25 of them. And the reason why these are the first 25 perfect squares is the fact that they come from the numbers 1 through 25 raised to the second power, or squared. Because we can get these 25 perfect squares by squaring numbers, we can take the square root of these numbers to get their square roots. So to summarize a little bit, if we take 7 and square it, we get 49, but when we take the square root of 49, we get 7. When finding the square root of 49, it's important to notice that you need 2 7s multiplied together to get 49. For another example, if we raise 12 to the second power, we get 144, so when we take the square root of 144, we need 2 12s to get there, so that's equal to 12. And for one more example, if we square 25, we get 625, and when we take the square root of 625, that's equal to 25 because 2 25s multiplied together equals 625. Now that we've gone over a little bit of background on simplifying radicals, let's try some practice problems together. In just a moment, we're going to go over 16 different practice problems on simplifying radicals that don't have perfect squares inside the radical. If you feel like this video is making sense so far and you're learning a little bit more about radicals, it would really help out this channel if you could give this video a thumbs up before we continue. When going over these 16 practice problems, feel free to pause the video whenever if you ever want to try them on your own or just to think a little bit. I encourage you to grab some paper, something to write with, and let's do some math together. For these first two examples, let's simplify these radicals of the square root of 40 and the square root of 63. Let's use some of our prior knowledge about prime factorizations to simplify these radicals since 40 and 63 aren't perfect squares. For the radicals to be fully simplified in this video, there can't be any perfect square factors inside of the radical. To simplify the square root of 40, let's start by drawing a prime factorization tree. Once you're finished with your prime factorization tree, go ahead and circle any primes, but circle any pairs first. Seeing as we have a pair of 2's, multiplying those together we get 4, and then the 2 and the 5 that don't pair up can multiply together to get 10. Pairing up the two 2's together we get 4, and pairing up the leftover numbers we get 10. Given that 4 is a perfect square and the square root of 4 is equal to 2, we can simplify this radical as 2 times the square root of 10, or 2 root 10. Since the only factors of 10 are 2 and 5 and neither of them are perfect squares, you can't simplify the square root of 10. For the square root of 63, go ahead and write a prime factorization tree and circle the prime factors of 3, 3, and 7. The two 3's pair up to make a perfect square of 9, and we can simplify this into the square root of 9 times the square root of 7. The square root of 9 is equal to 3, so we can write 3 root 7 as our answer. By writing the prime factorizations of these numbers, we can easily find pairs of prime factors to find perfect squares. Once we have perfect squares, we can take the square root of them, and whatever's left over stays under the radical. This is a great strategy for simplifying radicals. Here's two more examples. Let's simplify the square root of 32. And if you'd like to try it on your own first, go ahead and pause the video before we continue. It turns out the prime factorization of 32 is going to be 5 2's multiplied together. Combining the two pairs of 2's all together, 2 times 2 times 2 times 2 will equal 16, and we have a leftover 2 that doesn't have a pair. We can rewrite the square root of 32 as the square root of 16 times the square root of 2, and the square root of 16 is just equal to 4, so our answer here is going to be 4 root 2. Let's simplify the square root of 24 now. Drawing a factor tree, we get the prime factorization of 3 times 2 times 2 times 2, and we see the two 2's that paired together here make 4, and the leftover 3 and 2 make 6. We can rewrite the square root of 24 as the product of the square root of 4 times the square root of 6. 4 is a perfect square, so we can rewrite the square root of 24 as 2 times the square root of 6, or 2 root 6. And if you ever want to check to see if your simplified radical makes sense, go ahead and square the number that's on the outside and multiply by the number on the inside, and you should get the initial number that you started with inside the radical. By squaring 4 we get 16, and 16 times 2 is equal to 32, and by squaring 2 that's equal to 4, and 4 times 6 is equal to 24 that we started with. Let's try simplifying the square root of 180. Creating a prime factorization tree, we know that 180 is equal to 2 times 5 times 2 times 3 times 3. The 2's will pair together to make 4, and the 3's will pair together to make 9, and 4 times 9 is 36, and the 5 is left over. Based on this, we can rewrite the square root of 180 as the square root of 36 times the square root of 5. Keep in mind that whenever you multiply a perfect square by another perfect square, like 4 and 9, we always get another perfect square, like 36. Simplifying the square root of 180, we get 6 root 5. While 117 looks prime, remember your divisibility rules, and when you add up the digits of a number, if that sum is divisible by 3 or 9, then the whole number is divisible by 3 or 9. So 1 plus 1 plus 7 is equal to 9, so we know it's divisible by 3. Pairing up the 3's from the prime factorization, we can rewrite the square root of 117 as the square root of 9 times the square root of 13. The square root of 9 is equal to 3, so we can simplify the square root of 117 as 3 root 13. And if you'd like to, go ahead and see if these simplified radicals make sense. Let's try a couple more here. For the square root of 90, that's going to break down into 3 times 3 times 2 times 5, and the two 3's will pair together to make 9, so we can rewrite this as the square root of 9 times the square root of 10, and so the simplified radical is going to be 3 root 10. And for this next one, the square root of 529 looks scary, but if you remember this going forward, that's just equal to 23. It's a perfect square. For the square root of 135, if we break down 135, we get 5 times 3 times 3 times 3. Pairing together two of the 3's, we get 9, so we can write the square root of 9 times the square root of 15, and we can simplify that down to 3 root 15. And for the square root of 28, the prime factorization is going to be 2 times 2 times 7, and pairing together the 2's, we get 4 times 7, and the square root of 4 is 2, so we can write 2 root 7. For the square root of 150, the prime factorization is going to be 5 times 3 times 2 times 5, and pairing together the two 5's, we get 25, and the leftover 3 and 2 make 6, so we can write the square root of 25 times the square root of 6. The square root of 25 is equal to 5, so our simplified radical is going to be 5 root 6. Breaking down 162, we get 3 times 3 times 3 times 3 times 2, and pairing the 3's together we get 9, and the other 3's we also get 9, so 9 times 9 is going to be 81, so we have the square root of 81 times the square root of 2. The square root of 81 is equal to 9, so we can rewrite the square root of 162 as 9 root 2. For the square root of 243, we can break down 243 into 3 times 3 times 3 times 3 times 3, or 3 to the 5th power, and 4 of these 3's are going to pair together, and we're going to get 81 times 3, and the square root of 81 is 9, just like earlier, and we can write 9 root 3. 408, we can break that down into 3 times 3 times 2 times 2 times 3, and the two 3's pair together to make 9, and the two 2's pair together to make 4, and 9 times 4 is 36, so we can write the square root of 36 times the square root of 3, and that simplifies down to 6 root 3. 700 is going to break down into 5 times 5 times 2 times 2 times 7, and the two 5's pair together to make 25, and the two 2's pair together to make 4, and 25 times 4 is 100, so we have the square root of 100 times the square root of 7. Now 100 is a perfect square, so this can simplify down to 10 root 7. For 338, the prime factorization is going to be 13 times 13 times 2, and the two 13's pair together to make a perfect square of 169, so we have the square root of 169 times the square root of 2. The square root of 169, as we saw earlier, was equal to 13, so our simplified expression is going to be 13 root 2. And there we have 16 different examples, or 4 squared examples, of simplifying radical expressions that have square roots. I hope you found this strategy useful, where you use prime factorizations to find prime factors to pair up to find the hidden perfect squares inside each number. And once again, if you found this video helpful and you want to support the channel, giving the video a thumbs up really does help out a ton. As always, keep up the great work, and I'll see you in the next one.